Okay, so these are I guess they are the most important characteristics, okay? This is the relationship between the amplitude of the wave, which is something very physical and related to the amplitude of the velocity potential. This is the explanation why we use negative instead of positive or negative instead of positive. And this is what the K means, okay? So let me go back. The dispersion, oh no, I can do it here. Here. Before we deduce the dispersion relation said that omega squared is equal to kg. Now k, we're saying that it is equal to 2 pi divided by lambda. Okay, so here you see that as the wave is longer, the frequency is lower. Okay, higher frequency, higher or longer length of the wave, lambda, and you will have lower frequency. Okay, so that's something which should be in your memory. Okay, omega squared k equal to kg, and k is equal to 2 pi over lambda. So the longer the wave, the less frequency it has. And finally, the velocity, okay? So right now, we are looking at the disturbance of the free surface, and after a few minutes, after a few seconds, I'm sorry, you will see that this has moved, in this case, to the right, okay? And this ratio of how this moves to the right or to the left is what we call the celerity, okay? The celerity. In some cases, they call it phase velocity. Okay, in this case, it moves to the right. Now, how do we calculate it? Well, you can see that we can take the length, okay? Let's take the length equal to the wavelength. And let's see how much time it takes to complete or to advance this distance lambda. And for that, if you fix this point here, it will go up and down and up again in a time equal to the period, right? So what we can do is we can get a quotient between the lambda, that's the length of the wave, and the tau, which is the time to complete this cycle. Okay, now, again, tau is equal to 2 pi over omega. And then you will see that you have 2 pi and lambda, which is equal to k. And eventually, you will be able to demonstrate that this is equal to this. Okay? So the celerity is equal to the square root of k over g. G over k. Now, here we recall that k is equal to 2 pi over lambda. So, as the wave increases, the celerity of the wave also increases. Not linearly related. See, you see that this is a square root, but increases. Okay, but as the wave increases, the frequency decreases. Okay, in many cases, it looks like it is a contradiction, right? But yeah, as the wave increases, the celerity increases, but the frequency decreases. Okay, now the relationship between lambda and the celerity is not linear. It's the square root, but increases. Okay, so that's the problem with the tsunami. The tsunami is a wave which is very, very long. So the celerity is very high. Okay, and what happens is that the wave gets so much inertia that it can reaches the shore and advances up, destroying everything in his motion. Okay, that's the danger of the tsunami. Okay, so that's one thing that we want to calculate tomorrow. Okay, tomorrow we are going to do this. If this is the wave tank, okay, we're going to move this with a certain frequency. This is F, this is cycles per second. Okay, from here you can get omega, and we are fine. So what we're going to be doing is generating something like this. Okay, now from here to here, we have lambda. And what I'm planning to do is that you are able to check a point on the crest and see how much time it takes to advance a certain distance. Okay? The wavelength, the wave tank is about 8 meters long. Okay? But probably the distance, the useful distance is about 5 meters long. Okay, so hopefully in these 5 meters, you are able to see or to measure the time the wave takes to travel a certain distance, maybe 3 or 4 meters. Okay, so you will have, with the photograph, you will have lambda. The motion of the pistons, we will know how much it is. So we know F, we can measure lambda, and we can measure the time that the wave takes to advance a certain distance. So we have the celerity. So we will be able to check the wave dispersion relation and also the celerity expression. It is possible that since the the water depth is not very high, okay, this water depth is not very high, it is possible that this H influences the celerity, okay? And that's something that you could look for in the literature for the solution for that case, okay? Now, inside the domain, okay, in here, this is D, this is the domain, okay? There is another velocity, different than the celerity, okay? And this distance, we can calculate it, and that's what we're going to be doing now, okay? How do we calculate it? Well, we assume, remember, that this was a potential flow. So the velocity can be calculated using the gradient of the velocity potential. Okay, now, we know that phi is expressed as z0 e to the I omega t minus kx e to the kz. So we can differentiate this with respect to x and z. And these are the results. So this u is equal to the derivative of phi with respect to x. And this is the result of the derivative of phi with respect to z. Okay? And you see immediately that this is equal to that one. Now, here you have an I. Okay, so the result of this is a sine. Here this is real, so the result of this is cosine. And the rest is the same. Okay, that means that we can calculate the amplitude of the velocity with the square root of this squared plus w squared. And this is the result. The result is this. That means that if you are here and you are located in this point, okay? So this is equal to, let's call it minus D, for example. Okay, this is a constant, and you can draw this as a circle. Okay, so when the wave crest is here, the velocity is probably like this, pointing to the right. When it starts going to the right, then it starts, the velocity in this point is going down. When this is very low, the crest, I'm sorry, the throw, the velocity is pointing in the negative direction. And as it recuperates, it goes up and completes the cycle. So it's moving like this. And the amplitude here is this. Okay. As you go in more depth, you will have another circular trajectory, but with a lower amplitude. And this is typical. This is decreasing. And as we said, down here, basically, velocity is basically null. Okay? That's why I said before, right? When the e to the kz is very helpful to us, right? Because usually, basically, you get very low in the water, the effect of the wave, you don't feel it because the e to the kz helps you out. Okay. Is there any questions so far, people? Questions so far? No, everything is crystal clear. Good. Good. Now, that's the first point. The second point was to say a couple of words about the assignment, right? Okay. Can you see my PDF, Misayo?
Yes, doctor.
Okay, people. So let me say a couple of words about the last question, okay? No, this one here. Okay, now, what I want you to do is this, okay? Let's suppose that you have a wave train. Okay, this is X, this is Z. And let's suppose you have a tube here. Diameter and height, and yeah, height and length. Okay, so you know that phi in this case is equal to a bar e to the I omega t minus kx e to the kz. Okay, now if the diameter of this tube is very small compared with the wavelength, okay, we can assume that lambda is larger than d. In this case, you can calculate the pressure on any point here simply as rho phi of t. As simple as that. Okay, and you say, wait a minute, but the problem is that here you have the body, right? It's a solid body. You're gonna have reflection and all of that. Yes, it's true. But if this is correct, okay, the body is so small that basically the wave train passes by the body as there was nothing. Okay, and this is something that we call the Frode-Krylov. We will apply this in the next chapter. You will see when we study heave and pitch coupled. Okay, so basically that's the idea behind Frode-Krylov. Every time you see Frode-Krylov, that means that. See, you have a wave frame, you have a body, but the wave is so long that it's basically that it doesn't see, the wave doesn't see that there's anything in there, right? So there's going to be some reflection, but it's so small that we can neglect it. Okay, that it's as simple as that. Now, if you have phi, here you have phi, you can differentiate it, you can multiply by rho, okay? You can have the pressure on the surface, and you have to integrate it. So you have the pressure here, this is your surface, you have the pressure. The pressure is not going to be the same everywhere, right? So there's probably that there's some forces, some pressure here like this. I don't know. What's the distribution? You integrate it, and remember to multiply by n, that's the normal pointing inward. And what we need to do is you calculate the amplitude of the force in the x direction, of course. Questions?
Yes, doctor. In this problem, we need check that the satisfying of Laplace equation and no penetration, no?
No. You don't need to.
Only when I need check this the Laplace equation and not penetration.
Oh, in some cases, I ask you directly. For example, I give you a function, right? And I tell you, is this adequate to solve this problem in gravitational flow? And if I ask you this question, the first thing that you have to do is, yes, does it satisfy continuity? And then you have to check that. But
Thank you,
somebody tells you this is the solution for this potential flow, it's affirming. So he did it before. Yeah, in this case, you don't need to check. But it's a good idea to do it. Yeah, I mean. Okay, so let's assume that it is water very deep. So again, on the deep floor, you have to check. I mean, it's a good idea to do it, to check that the velocity in the vertical direction is null, is zero. Okay, the free surface, remember, free surface, immediately you think about the dispersion relation. And these people were really smart. What they did was they left this K constant, and they set it up in certain way, omega squared equal kg, so that if you take this assumption, you satisfy the free surface boundary condition. So it's basically that. The dispersion relation is a special relation in order to satisfy the free surface boundary condition. Okay, the last question, people, in case the last question. Okay, here, in this case, what you have to do is you have to look for in the literature. Okay, so you have the free surface, but in this case, the water depth is here. And you see that the depth is not very large. So in this case, let me draw it again. So you have a lambda here. Okay, and the water depth is but now H is not very large. So the function to solve this problem is not the same as the one before. It's different. So I don't want you to develop the solution because we have spent only 5 or 6 hours to study this hydrodynamics. So I'm not going to give you that problem. But I want you to look for in the literature and find a solution for this. So it's going to be similar, but not the same as the one that we had before. Similar to this one. It's not the same. It's not the same. When you get this, that's going to be satisfied in here, in the domain. Again, to satisfy the boundary condition on the free surface, you have to satisfy or you have to develop a new dispersion relation. Okay. On the bottom, you have to satisfy the no penetration condition because we assume it's solid body. Any question? No questions. Okay, people. So,
Director.
Yeah.
I have a question, but it's about the second one. And I was trying to plot the velocity, potential velocity function.
Yeah.
In Excel, but I don't know what to start to variate because I tried to do the exercise that you show in classes, but I couldn't do it. So I want to ask you how to do that.
It's exactly as I said before. I mean, what I do here is what you suggest is always try to convert from the rectangular to polar coordinate system. This is a 2D problem. So what I do is exactly as I try to explain it to you. If this is X and Y, okay, what I do is I'm going to fix phi. So I'm going to draw a curve on which the value of phi is constant. Okay, so what I do is, okay, I have a value for phi. What I do is I fix the value of theta. This is fixed. And then if I have these two, I try to find R. So that means that from here until here, that's the distance which solves this equation. Okay, now this is a nonlinear equation, right? So you have to apply what you learn in numerical analysis. Do you remember what algorithm you can use in order to solve this nonlinear equation? Do you remember? But anybody remembers the name of an algorithm to solve for a nonlinear algebraic equation? People, turn on your cameras. Come on. I don't want to talk to me, talking to myself. Do you remember the name of an algorithm to solve nonlinear equations?
Bisection, doctor.
Pardon me?
Method of bisection.
Bisection, yeah, that's one. That's one. But it's very inefficient. Anybody else? There was a much more efficient way to calculate.
Doctor, it's possible we have only value satisfy the equation.
Need some wraps.
It's possible to have one value to satisfy the equation. This is.
I don't understand your question. I mean, what you have to do is you have to see, in this case, you have 1 point. And then what you do is you change theta. You change theta, and by changing theta, you find another value of r, the corresponding value of r. That means that, okay, but you keep phi. Okay, so what you do is, in this situation, okay, now let's find another value, but with different value of theta. So this is the new value of theta. If this changes, phi is the same. Phi is the same. Okay, but theta changes. So the solution is going to be different in general. So the R is going to be different. Okay, so you have a different R, so this value will be different. So you have that the function phi is constant. You have 2 points, here and here. If you have several other points, then you can draw a curve on each one of these points. And that's the way you do it. Mr. Zamora? Okay, somebody said Newton-Raphson. Yes. It's much more efficient. Much more efficient. And you have to differentiate, that's all. I mean, the derivative of a function is something which is extremely easy to calculate. Extremely easy to calculate. Okay, people, for tomorrow, we're going to start at 8. And what we're going to be doing, tonight, I'm going to change the lab procedure, since we're going to be using the water tank. We're not going to use what I was planning at the beginning. Okay, so as I said before, what we're going to be doing is we have a tank, okay, here, okay, I have some guides. We can move it in this direction. The water level. So what we're going to be doing is this motion is going to be controlled. So we call it an amplitude and a frequency. Please remember, this is the amplitude of the motion in the horizontal direction. As a result of that, we're going to have a wave which is going to be traveling with certain celerity. The length okay, the celerity, the length related to the frequency, those are the characteristics that we want to check. So the frequency is equal to kg. Celerity is equal to square root of g over k. Okay, so what I'm planning to do is that you measure. Okay, we have some rules. So you can have a certain distance. And what we are planning to do is 2 or 3 people can do different measurements. So when you have a crest about here, you start your chronometer and you advance, and the same crest goes through this point, you stop the chronometer. Then you have the time, you divide this distance by the time, and you will get the celerity. Same time, somebody else, we can put another scale on the glass, and you can take a picture. Picture in this scale, okay, scale, you can draw this and calculate the lambda. So you will have the distance, the lambda, time to calculate the celerity, and the frequency. That's because we have the information from the shaker. And then we can do this, for example, for 2 or 3 minutes. And then what we can do is we can change the frequency to a different value, taking a long enough time in order to let the surface to settle down. And then it start again shaking, but with a different frequency. So the celerity, the frequency, and the wavelength are going to be different. And then we can plot these parameters theoretically and experimentally, and let's see if there's any relationship. Questions? Questions? No questions. Okay, so tomorrow, those of you who can come, that's going to be at 8 in CMAR Lab. On Thursday, you're going to have the quiz in the afternoon. I'm planning to have it at 2, from 2 to 4. Okay. It's closed book. Hopefully by tomorrow afternoon, tomorrow night, I will post last year's exam. So you will be able to see what kind of questions can you expect in the evaluation. Okay. Yeah, there is no secret on that. But it's closed book. Definitely. 2 hours and that's. And on Friday, as I said, we agreed, each one of you has to make a short, it's not a presentation, it's just an explanation of either one of the problems in homework 1 or homework 2. Yeah, I'm going to give you 2 or 3 minutes for that, for each one of you. And I would like you to help me because I would like to do it in the morning. Okay, because in the afternoon, I would like to play basketball. If you want to come, you are welcome. If you want to come, there is no problem for me because my head is really banging me right now. Okay, so we can start by, say, 10:30 or so. And we can go maybe 1 hour or something like that. And the rest, we can do it from 1 to 2. And then you can go on and do the second part of the test. The second part of the test is going to be about vibration, the force vibration. So you have to prepare a report on those 2 lab experiments. Questions?
The lessons about of the material of chapter 1 and 2, right?
Yes. Yes, 1 and 2. That's all. That's enough.
In the quiz, you give us the formulas.
Remember,
Maybe.
the objective of this course in some cases is analyze. When you have to analyze something, okay, you have to do, you can do several things, but there are two extreme things that you can do. If you want to analyze something, then you have to go deep enough and you have to be able to deduce something. For example, if I give you a relation and I ask you to deduce another thing, you don't have to remember that in your memory, but you have to remember how you did it, how to deduce the expression. Or you need to apply these results. For example, if I want you to, I don't know, calculate the pressure distribution, yes, I have to give you the phi equation. You don't have to remember that. But remember, if you are to analyze something, that you have to be able to deduce or you have to be able to apply. If I need to check that you are able to deduce, then I'm not going to give you the expression. What I'm going to ask you is deduce the expression for that. If I need you to test if you are able to apply, then I'll give you the expression and I will tell you, I will ask you, apply this in this situation. And you have to show me that you indeed can take that expression, do some manipulation, and finally apply it in the case I'm asking for. So you have to cover both situations.
Okay, doctor, thank you.
No problem. People, remember that I asked you 3 weeks ago that you have to do this Excel module in EDX. This course is serious. This course is serious. The first day of classes, I told you, there is no questions about it. Every homework in this class is obligatory. If you do not complete the homework, the assignments, you are in trouble in this class. The first day of class, I told you, this is a serious class. So you have to give me proof that you have taken this module, because that was an assignment. I did not give you the freedom to do it or not. You have to do it. Okay? Okay, people. So if there's nothing else, then I'll see you tomorrow. For those of you who are coming, twice I'll see you when I see you on Thursday. Okay? No questions?
Doctor, it's about the actual course. I finished the course, but in the link say that then you up a homework to do in Excel, but because we don't have any for send evidence.
Yeah, I don't have energy to do that. The thing is this, were you able to capture any part of the class during any of the sessions that you open?
Yes, when you complete the session,
yeah, that's it. That's all.
And I have to send.
Yeah, not to me, please. I have enough. Send it to Giovanna Kinde, please.
Thank you, doctor.
Yes, no problem. No problem. Any other question, people? Okay, bye-bye now.